Okay, let's look at another example with trig substitution. So this one we've got the form x squared plus a squared. So there's a they have it in the other order, a squared plus x squared, but there's this form right here. They suggest that you replace x with a times tangent theta. So let's work on making that substitution. Let's work on making x needs to get replaced by a, which is 2, so 2 tangent theta. And that means that dx will have to get replaced by 2 secant squared theta d theta. Okay, let's work on making our substitutions and see how this integral turns out. So we've got 5 over x squared, so x squared would be 4 tangent squared. And then square root of x squared again, which is 4 tangent squared theta plus 4. Dx is the same thing as 2 secant squared theta d theta. Okay, we've made the substitutions. Let's see if the integral is actually any better than it was before. The important part, of course, is this square root here, and the usual trick applies here, which is to factor the 4. As I rewrite this, I'm going to clean up the top a little bit too. This is all over 1, so this stuff goes to the top. So on top we've got 10 secant squared theta. And I'm just going to leave the d theta out on the end. On the bottom we've got 4 tangent squared theta, and inside the square root I'm going to factor the 4 out. Leaves me with tangent squared theta plus 1. And there's where the magic happens, right? Because we know that tangent squared theta plus 1 is the same thing as secant squared theta. So let's see, let me go up over here. Rewrite the integral again. So we've got 10 secant squared theta over 4 tangent squared theta. The stuff inside the square root becomes 4 times secant squared theta. And the whole point of doing these substitutions is to get rid of this square root. And the thing inside the square root now you can evaluate. So inside the square root, everything else is going to stay the same here. Inside the square root, that becomes 2 secant theta. And on top, we've got 10 secant squared theta, d theta. I don't exactly know how this is going to work out, but it's starting to feel like maybe it is going to work out. So let's see what's going on here. We've got secant squared that we can cancel with a secant there. We've got a 2 and a 10 that can turn into 5. Okay, let's rewrite again. Five secant theta over 4 tangent squared theta d theta. And this still maybe isn't immediately obvious. But let's keep going and doing some trig simplification here. And actually, I'm just going to pull the 5/4 out front. So 5/4 secant. Let's go all the way back to basics. Secant is 1 over cosine. Tangent is sine over cosine. So we've got fractions divided, we can flip. Say we've got 5/4 integral. See, flip the bottom fraction, so the top will be cosine squared times 1. The bottom will become cosine theta times sine squared theta d theta. We're starting to get there. The cosines on the top cancel one of the cosines on the bottom. So we are at 5/4 integral cosine theta over sine squared theta d theta. And I know we've already done one substitution on this problem, but now's the time where we would pick out a u substitution normally, just to, if this had been our starting integral right here, you would pick a u substitution. Let's see, let me get a different color going here. So let's say that u sine theta du is cosine theta d theta. And this integral becomes 5/4 integral u squared on the bottom, and the whole thing on the top is, all of that is du, so maybe I'll put a 1 there and a du out there. And we've got 5/4 integral u to the -2 du, and you know what? We can finally actually do an integral here. All this has just been like algebra and trig, essentially. We actually get to do some calculus now. So let's integrate this thing. So we've got 5/4 u to the -1 divided by -1, so let's put the negative out there, plus c. We're not done yet because the original variable wasn't u. So u is the same thing as sine theta. And sine theta also was not the original variable. X was the original variable. So to get this all the way back, theta back to x, look at that relationship right there. And you can solve that for theta. It gets a little bit messy. This is the point where I prefer to draw a triangle. And I think you should prefer this too. This will work out nicely for us. So check this out. We've got x equals 2 tangent theta. And I just want a way to turn sine theta back into some x stuff. Let me go ahead and solve this for tangent. That'd be my first step anyway, even if I was trying to solve for theta and get an inverse tangent thing. But instead, let's draw a triangle. Tangent theta, x over 2. So let's draw a triangle. There's theta. Tangent theta. And here's where you get to go back and remember, if you have forgotten it, the definition of tangent as far as triangle goes, which is the opposite over the adjacent. So tangent of theta. So there's theta in my little picture. So tangent is opposite over adjacent. That's my triangle. And really, for my substitution right here, I just need to know about sine of theta. So sine of theta is opposite over hypotenuse on this same triangle. The opposite is x. The hypotenuse I still need to work out, but this is a right triangle. So I can work out the hypotenuse. Just a squared plus b squared equals c squared. So the hypotenuse ends up being the square root of 4 plus x squared. So all that to say that when I finally go back from my green theta answer, I finally go back to x's again, I can say my final answer here, -5/4 sine of theta. Sine of theta is opposite over hypotenuse. Plus c. And we are finally done. Actually, this -1 exponent here means I should probably just flip this fraction and get rid of that -1 exponent. So I think that would probably be your very last step. So the very last version of the answer would look like 5 square root of 4 plus x squared all over 4x, that's negative, plus c. All right, we wrapped our way all around the whiteboard here to get that answer. Such a simple answer for such a long process. But again, I want to point out here that most of the process was algebra and trig. Very little of it was actual calculus. We did do an integral. It did need a little u substitution. But then even most of the work after that was back substituting, right? It was algebra again of turning u back into theta and turning theta back into x. And the key there, I think, is to, if you do need to turn theta back into x, is to draw a triangle. And I strongly recommend that rather than trying to solve this for inverse tangent and trying to figure out what sine of inverse tangent is. That gets to be a mess. All right, see what you can do with those trig substitution problems.